Before the sound barrier was broken, it was feared. For pilots and engineers of the early 20th century, the speed of sound was not simply a number on an equation. It was an invisible wall in the sky, a violent threshold that aircraft could approach but seemingly never cross without paying a price. As airplanes accelerated toward this limit, they began to behave in ways that defied intuition and experience. Control surfaces stiffened or became unresponsive. Shock waves formed abruptly along wings and fuselages. Aircraft shook, pitched, and rolled as if gripped by an unseen force. Several pilots died pushing too close to this boundary, and the phenomenon earned a chilling name: the sound barrier. By the final years of World War II, aviation had reached a crossroads. Piston-engine aircraft were approaching their absolute performance limits, and even the newest jet-powered fighters were beginning to encounter the same mysterious aerodynamic problems. Engineers knew that speed was the future. Faster aircraft meant military superiority, shorter flight times, and a fundamental transformation of how distance itself was understood. But speed also revealed how incomplete humanity's understanding of high-velocity flight truly was. The challenge was not simply about going faster. It was about surviving the journey. At transonic speeds, those just below Mach 1, airflow over different parts of an aircraft reached the speed of sound at different times. Shock waves formed unevenly, disrupting lift and dramatically increasing drag. Pilots reported nose-down pitching moments, violent buffeting, and sudden loss of control. Many believed the aircraft itself would tear apart if pushed any further. Some scientists openly questioned whether controlled supersonic flight was even physically possible for a piloted aircraft. Yet the necessity to find the answer was overwhelming. In the aftermath of World War II, the United States emerged with unmatched industrial capacity and an urgent need to maintain technological dominance. The dawn of the Cold War loomed, and with it the realization that future conflicts would be decided not only by numbers, but by speed, altitude, and intelligence. Aircraft capable of outrunning defenses, climbing higher than enemy interceptors, and gathering data beyond reach became strategic imperatives. The U.S. Army Air Forces, soon to become the U.S. Air Force, recognized that guessing was no longer sufficient. Supersonic flight could not be achieved safely through incremental improvements to existing fighters. It required a radical shift in approach, a purpose-built experimental aircraft designed not for combat, not for transport, but for pure knowledge. This was the birth of the X-plane philosophy. Unlike operational aircraft, X-planes were flying laboratories. Their sole purpose was to explore the unknown regions of aerodynamics, propulsion, and structural limits. Every rivet, every surface, every instrument served the pursuit of data. The aircraft would not be judged by range or payload, but by what it could teach engineers about the physics of flight at extreme speeds. At the center of this effort stood a partnership that would define modern aerospace research. The National Advisory Committee for Aeronautics, or NACA, the predecessor to NASA, joined forces with the U.S. military and American industry. Companies like Bell Aircraft were tasked with transforming theoretical equations and wind tunnel predictions into real machines capable of flying into regimes no human had ever experienced. Bell Aircraft's engineers understood immediately that traditional design logic would not work. Swept wings, common in later supersonic aircraft, were still poorly understood. Instead, they chose a radical solution based on the most stable shape known at high speeds: the bullet. The resulting aircraft would be compact, thick-skinned, and brutally simple. It would be carried aloft beneath a bomber and released at altitude, conserving fuel and avoiding the dangers of takeoff and climb in an experimental machine. This aircraft would become the Bell X-1. Powering it required equally unconventional thinking. Jet engines of the era lacked the thrust-to-weight ratio necessary for sustained acceleration through the transonic regime. Instead, engineers turned to a rocket engine, capable of delivering massive thrust for a short duration. Fueled by alcohol and liquid oxygen, it offered raw, explosive power, enough to push the aircraft beyond the sound barrier in a controlled dive. But engineering alone was not enough. The aircraft would still need a pilot willing to ride it into the unknown. Test pilots occupied a unique place in aviation history. They were not daredevils chasing adrenaline, nor were they traditional combat aviators. They were disciplined professionals, trained to observe, report, and remain calm as machines approach failure. Their job was not to survive by instinct, but to survive by procedure. Among them was a young pilot named Chuck Yeager. Yeager was not an engineer by training. He did not possess a university degree, nor did he speak in equations. What he possessed was an extraordinary feel for aircraft, honed through combat experience during World War II. He understood airplanes not as abstractions, but as physical systems, how they moved, how they warned of danger, and how they responded when pushed beyond comfort. His background made him ideal for a task where instinct and discipline had to coexist. The decision to attempt a supersonic flight was not framed as a heroic gamble. It was a calculated experiment, the culmination of years of research, failures, and incremental progress. Every sensor on the X-1, every structural reinforcement, every emergency procedure was designed to answer one question. Could a human-controlled aircraft pass through Mach 1 and remain stable on the other side? The world before this moment was defined by limits. Speed limits, structural limits, psychological limits. Aircraft designers worked within boundaries they did not fully understand, constrained by phenomena they could observe but not yet conquer. Breaking the sound barrier was not simply about achieving a record. It was about redefining those boundaries entirely. If successful, it would unlock a new era of aviation. If it failed, it would reinforce the belief that some frontiers were never meant to be crossed. The stage was set high above the California desert, where clear skies and vast empty expanses provided the ideal laboratory for pushing flight to its extremes. There, suspended beneath a bomber, a small orange aircraft waited, an embodiment of engineering ambition and human resolve, poised to answer a question that had haunted aviation since its earliest days. The journey towards supersonic flight was no longer theoretical. It was about to become real. The aircraft that would attempt this crossing was deceptively small, but every inch of its structure represented a confrontation with the unknown. The Bell X-1 was not designed for elegance or versatility. It was designed to survive forces that no piloted aircraft had ever endured. Its fuselage was thick and rigid, shaped like a .50 caliber bullet because ballistics engineers already knew that such a form remained stable beyond the speed of sound. This was not coincidence or aesthetics. It was physics applied without compromise. Inside, the cockpit was cramped and brutally utilitarian. There was no pressurized cabin in the modern sense. Instead, the pilot wore a pressurized suit, an early precursor to spaceflight gear, to survive the thin air at altitude. The controls were manual, heavy, and unforgiving. At near supersonic speeds, aerodynamic forces grew so extreme that conventional elevators lost authority. Engineers addressed this by introducing an all-moving horizontal stabilizer, a revolutionary concept at the time. Rather than deflecting a small control surface, the entire tailplane pivoted as one piece. This single design decision would later become standard on nearly every supersonic aircraft ever built. The risks were not abstract. They were immediate and personal. Rocket propulsion introduced dangers unknown to jet or piston aircraft. Liquid oxygen was volatile, unforgiving, and lethal if mishandled. The engine produced enormous thrust, but only for a few minutes. Every second mattered. Fuel flow had to be managed precisely, acceleration carefully staged, and the aircraft's attitude controlled with absolute discipline. There would be no margin for improvisation. Compounding the danger was uncertainty. Wind tunnel data suggested that drag would spike dramatically near Mach 1, potentially trapping the aircraft in a region of uncontrollable turbulence. Some theorized that shock waves would cause irreversible structural failure. Others feared that control reversal could drive the aircraft into a fatal dive. No one knew which prediction would prove correct, because no one had ever brought back reliable data from the other side of the sound barrier. The financial and institutional stakes were equally high. The X-1 program represented a significant investment at a time when military budgets were being reshaped for a new geopolitical reality. A failure would not only cost money and equipment, but potentially lives and credibility. Success, however, would place the United States decisively ahead in the race to master high-speed flight, with implications reaching far beyond aviation itself. Chuck Yeager understood the risks intimately, though he rarely spoke of them in dramatic terms. In the days leading up to the historic flight, he suffered a setback that could have ended his participation entirely. During a horseback riding accident, Yeager fractured 2 ribs. Rather than report the injury and risk being grounded, he concealed it. The pain was severe, and it compromised his ability to close the X-1's heavy cockpit hatch. A fellow engineer quietly modified a broom handle, allowing Yeager to lever the hatch shut once inside. It was an improvised solution to a problem that no flight manual could anticipate. On the morning of the flight, the desert air was calm. The X-1, painted a vivid orange for visibility, was carried aloft beneath a modified B-29 bomber. This method of launch was itself a calculated necessity. Taking off under rocket power was impractical and dangerous. By releasing the aircraft at altitude, engineers conserved fuel and allowed Yeager to begin the flight already near the edge of the unknown. At the designated height, the X-1 dropped free. For a brief moment, it fell silently, stabilizing itself before Yeager ignited the rocket engine. The thrust was immediate and relentless. Acceleration pressed him into the seat as the aircraft surged forward. Mach numbers climbed steadily. The familiar buffeting associated with transonic flight began to appear, but it was different this time. Instead of growing worse, it stabilized. As the aircraft approached Mach 1, something unexpected happened. The violent shaking that pilots had long associated with the sound barrier diminished. Control inputs became smoother. The aircraft did not tear itself apart. It did not pitch uncontrollably. The feared wall in the sky did not manifest as an explosion or a catastrophe. Instead, it dissolved. The X-1 passed Mach 1. On the ground, observers did not hear an immediate sonic boom. The sound arrived later, detached from the moment itself, rolling across the desert like distant thunder. In the cockpit, Yeager experienced something far more profound than noise. He felt stability. The aircraft, now supersonic, flew more cleanly than it had moments before. This was the moment when myth gave way to measurement. Data streamed from onboard instruments, recording pressures, temperatures, and structural loads. The numbers confirmed what Yeager already sensed instinctively. Controlled supersonic flight was not only possible, it was sustainable. The sound barrier was not a barrier at all, but a transition, dangerous only when misunderstood. Yeager continued the flight, pushing the aircraft slightly beyond Mach 1 before shutting down the engine and gliding back toward Earth. The rocket fuel was exhausted quickly, as expected. There would be no victory lap. The mission's success lay not in duration, but in proof. When the X-1 landed, history had already shifted. The immediate impact was subtle. There were no live broadcasts, no public announcements, no triumphant headlines. The achievement was classified, discussed quietly among engineers, pilots, and military planners. But within those circles, its significance was unmistakable. The fundamental assumptions governing aircraft design had been rewritten in a single flight. Supersonic flight was no longer theoretical. It was operational reality. And with that reality came consequences that would ripple outward across technology, economics, and global power for decades to come. What followed that flight was not celebration, but transformation. Once the data from the X-1 was analyzed, engineers realized that the true breakthrough was not merely exceeding Mach 1, but understanding why the aircraft remained controllable beyond it. The feared exponential drag rise did occur, but it peaked and then diminished. Shock waves, once seen as chaotic and destructive, could be predicted, managed, and even exploited through proper shaping and control strategies. The atmosphere had not imposed a hard limit. Human design assumptions had. This realization marked a profound shift in aerospace engineering. Aircraft were no longer constrained by conservative margins rooted in fear of the unknown. Instead, designers began to treat the transonic and supersonic regimes as solvable engineering problems. The principles validated by the X-1 immediately influenced wind tunnel testing, computational methods, and structural design philosophies across the aviation industry. The all-moving tail, once an experimental gamble, became a cornerstone of high-speed aircraft control. Engineers recognized that conventional hinged elevators were fundamentally inadequate at supersonic speeds due to shock-induced airflow separation. By pivoting the entire stabilizer, control authority could be preserved even as airflow characteristics changed dramatically. This single insight would echo through generations of fighters, bombers, and experimental aircraft. Equally important was the confirmation that rocket propulsion, while impractical for everyday aviation, was invaluable for research. Rocket-powered aircraft allowed engineers to decouple acceleration from atmospheric limitations, creating brief but crucial windows to explore extreme flight regimes. This approach would later become essential not only for aircraft development, but for spaceflight itself. The success of the X-1 redefined the relationship between pilots and machines. Supersonic flight demanded precision, discipline, and trust in engineering. There was no room for intuition-based flying alone. Every maneuver had to respect the physics revealed by data. Test pilots became extensions of the engineering process, executing carefully planned profiles rather than improvising responses to unexpected behavior. As the implications of supersonic flight spread, they began reshaping military doctrine. Speed was no longer just an advantage. It became a strategic multiplier. Faster aircraft could intercept threats before detection, penetrate defended airspace, and escape retaliation. Altitude and velocity combined to create new forms of dominance, redefining how air superiority was achieved and maintained. This paradigm shift arrived at a critical moment. The Cold War intensified, and with it the race for technological superiority. Supersonic fighters moved rapidly from experimental concepts to frontline necessities. Aircraft such as the F-86 Sabre and later generations of interceptors drew directly from the aerodynamic lessons proven by the X-1. Swept wings, refined airfoils, and advanced control systems all traced their lineage back to that single flight over the desert. Beyond the military sphere, the psychological impact was equally significant. For the public, the sound barrier had symbolized an ultimate limit. Breaking it challenged deeply ingrained perceptions about human capability. It reinforced a growing belief that technology, guided by disciplined engineering and scientific rigor, could overcome obstacles once thought insurmountable. This belief carried economic consequences. Governments increased investment in aerospace research, recognizing it as a driver of national prestige, industrial growth, and long-term security. Universities expanded aeronautical engineering programs. Entire supply chains emerged to support high-speed flight, from advanced metallurgy to precision manufacturing. Supersonic research became a catalyst for innovation far beyond aviation alone. The X-1 itself did not evolve into an operational aircraft, nor was it intended to. Its role was to open the door. Subsequent X-planes pushed further, exploring higher Mach numbers, greater altitudes, and more extreme conditions. Each built upon the foundational knowledge that the sound barrier was not an endpoint, but a gateway. Chuck Yeager's flight became a reference point rather than an isolated achievement. It demonstrated the power of methodical experimentation over speculation. Where earlier pilots had encountered chaos, structured engineering revealed order. Where fear had dominated design decisions, data introduced confidence. In the years that followed, supersonic flight reshaped not only aircraft, but timelines. Distances shrank, response times compressed. The world began to move faster, both literally and strategically. What once took hours could now take minutes. What once seemed unreachable was now a design challenge waiting to be solved. Yet perhaps the most enduring impact was philosophical. The sound barrier had existed as much in the mind as in the atmosphere. Breaking it proved that limits are often artifacts of incomplete understanding. When confronted with rigorous analysis, disciplined testing, and the courage to act on evidence, those limits can dissolve. The desert flight of a small orange aircraft thus became more than a milestone in aviation history. It became a case study in how humanity advances, not by reckless daring, but by aligning ambition with knowledge. Supersonic flight was no longer an anomaly. It was the beginning of a new normal. As supersonic flight transitioned from experiment to foundation, its influence spread outward in widening circles that reached far beyond the dry lake beds of the American desert. The Bell X-1 itself was never intended to become a production aircraft, nor was it refined for operational use. Its true value lay in what it revealed, not in what it could carry or how far it could fly. It was a tool of discovery, and the knowledge it generated reshaped aviation at every level. Once the sound barrier had been crossed and measured, engineers no longer viewed Mach 1 as a cliff edge. It became a reference point, a known transition that could be planned for, designed around, and ultimately optimized. This mental shift was as important as any aerodynamic breakthrough. Aviation had entered an era in which speed was not merely increased incrementally, but explored systematically. The immediate successors to the X-1 built directly on its lessons. Later experimental aircraft pushed well beyond Mach 1, then Mach 2, and eventually into hypersonic territory. Each program refined understanding of shock wave formation, pressure distribution, structural resonance, and thermal loading. Supersonic airflow was no longer mysterious. It became a design environment with its own rules, constraints, and opportunities. One of the most enduring technical legacies of the first supersonic flight was the transformation of control system design. The all-moving horizontal stabilizer, proven effective on the X-1, became a defining feature of high-speed aircraft. Engineers had learned that small hinged control surfaces were fundamentally inadequate when shock waves disrupted airflow. Full-flying surfaces restored authority and predictability, allowing pilots to maintain control even as aerodynamic conditions shifted dramatically. This principle became universal, appearing on fighters, bombers, and experimental aircraft around the world. Wing design evolved just as profoundly. Early supersonic research demonstrated that thickness, sweep, and planform geometry were critical in managing wave drag. Swept wings delayed the onset of shock waves, reducing drag and stabilizing airflow at high speeds. Thin airfoils minimized pressure disturbances, while careful shaping reduced structural stress. These concepts reshaped not only supersonic aircraft, but also improved the efficiency of subsonic designs, which benefited from reduced drag and smoother airflow. Fuselage design underwent a similar revolution. Engineers discovered that abrupt changes in cross-sectional area intensified drag near Mach 1. The solution, later formalized as the area rule, emphasized smooth, continuous shaping along the length of the aircraft. This insight allowed designers to significantly reduce drag without increasing engine power, demonstrating once again that understanding physics could achieve what brute force could not. Materials science advanced in parallel. Supersonic flight introduced thermal challenges that earlier aircraft had never faced. At high speeds, air friction heated surfaces enough to weaken conventional aluminum alloys. Engineers responded by developing new materials and manufacturing techniques. Titanium, stainless steel, and high-temperature composites found their way into airframes, engines, and structural components. These innovations extended aircraft lifespans, improved safety margins, and laid groundwork for future aerospace applications. The military implications of these advances were immediate and far-reaching. Supersonic fighters became central to air superiority doctrine. Speed enabled rapid interception, reduced vulnerability, and expanded operational reach. Aircraft could now outrun threats, dictate engagement terms, and operate in environments that had previously been inaccessible. Supersonic capability became a baseline requirement rather than an exceptional feature. Strategically, this shift altered the balance of power. Nations that mastered supersonic flight gained disproportionate influence, not only in combat scenarios, but in deterrence and intelligence gathering. High-speed reconnaissance platforms emerged, capable of penetrating defended airspace and escaping before interception. The relationship between speed, altitude, and survivability became a defining equation of Cold War aerospace strategy. The influence of supersonic research extended beyond aircraft alone. Rocket propulsion experiments conducted in parallel with high-speed flight programs directly informed missile development. Understanding how vehicles behaved at extreme velocities and during atmospheric transitions proved essential for ballistic trajectories and re-entry physics. The boundary between aviation and spaceflight began to dissolve, unified by shared aerodynamic and structural challenges. In this sense, the first supersonic flight can be seen as a precursor to the space age. The methodologies refined during X-plane programs, incremental testing, data-driven design, and acceptance of calculated risk became standard practice in astronautics. Capsules, boosters, and re-entry vehicles all benefited from knowledge first gained by pushing aircraft beyond Mach 1. Culturally, The impact was unmistakable. Supersonic flight captured the imagination of the public as a symbol of progress and modernity. The sonic boom, once feared and poorly understood, became a powerful auditory marker of technological achievement. Aviation assumed a new role in the collective consciousness, representing not only transportation, but human ambition itself. Pilots who flew supersonic aircraft were no longer perceived merely as operators of machines. They became symbols of precision, discipline, and trust in engineering. Their role reinforced a broader narrative that mastery of complex systems required cooperation between human judgment and technological rigor. Supersonic flight did not diminish the importance of the pilot. It elevated it. Economically, the ripple effects were substantial. Governments invested heavily in aerospace research, recognizing its multiplier effect across industries. Advances in aerodynamics drove improvements in manufacturing, computation, instrumentation, and materials. Supply chains expanded, universities grew specialized programs, and a new generation of engineers was trained to think beyond traditional limits. Commercial aviation, while constrained by cost, fuel efficiency, and noise considerations, was not immune to these influences. Even aircraft that never approached Mach 1 benefited from supersonic research. Improved understanding of airflow reduced drag and fuel consumption. Enhanced structural analysis increased safety margins. Advanced materials improved durability and performance. Supersonic flight reshaped aviation as a whole, not just its fastest segment. Yet perhaps the most enduring legacy of the first supersonic flight was methodological rather than mechanical. The X-1 program established a model for confronting the unknown that would be replicated across science and engineering. Problems were defined precisely. Experiments were designed to generate knowledge, not publicity. Risk was acknowledged, managed, and justified by potential insight. Results were shared, analyzed, and applied systematically. This approach contrasted sharply with earlier eras of aviation, where progress often relied on trial and error, individual intuition, and incremental modification. Supersonic research demonstrated the power of coordinated effort, where pilots, engineers, scientists, and institutions worked toward a common objective grounded in evidence. Chuck Yeager's role within this framework became emblematic. He was not celebrated simply for bravery or personal daring. He was respected for his discipline, consistency, and ability to execute precisely what the data demanded. His success reinforced the idea that technological breakthroughs are rarely the result of lone heroics. They emerge from systems designed to align human skill with scientific understanding. As decades passed, supersonic flight became normalized within aerospace engineering. Designers no longer asked whether an aircraft could exceed Mach 1. That question had been answered definitively. Instead, they asked how efficiently it could do so, how safely, and under what operational constraints. The challenge evolved from possibility to optimization. In that evolution lies the true legacy of the first supersonic flight. It did not close a chapter in aviation history. It opened a new one defined by confidence in method, respect for physics, and willingness to challenge assumptions. The sound barrier, once feared as an insurmountable wall, had been reduced to a milestone, not because it was ignored, but because it was understood. And in aviation, understanding is what turns limits into launch points. By the time the implications of the first supersonic flight were fully understood, the moment itself had already receded into history. What remained was something far more powerful than a record or a headline. It was a lesson about how progress is achieved when ambition, discipline, and engineering align with purpose. The breaking of the sound barrier did not usher in an age of reckless speed. Instead, it imposed a new level of responsibility. Supersonic flight demanded respect for physics at its most unforgiving. At high Mach numbers, small errors grew into catastrophic failures. Structures were stressed by heat and pressure. Control margins narrowed. Every design choice carried consequences that could not be negotiated away by skill alone. In this environment, engineering rigor became non-negotiable. This reality reshaped the culture of aviation. Design reviews grew more conservative in appearance, but more daring in intent. Engineers learned to push boundaries not through guesswork, but through modeling, testing, and validation. The lesson of the X-1 was clear. The unknown is not conquered by courage alone, but by understanding earned through methodical exploration. The sound barrier also changed how humanity perceived its relationship with the atmosphere. Flight was no longer limited to what the air would comfortably allow. It became an active negotiation with natural forces, compressibility, shock waves, thermal loads, that could be managed through knowledge. The sky ceased to be a passive medium and became an environment with layers, regimes, and thresholds, each demanding its own solutions. This shift had implications far beyond aviation. Supersonic research influenced how engineers approached complex systems in general. The idea that extreme conditions could be studied safely through incremental experimentation became foundational across disciplines. Nuclear engineering, space exploration, and high-energy physics all adopted similar philosophies. Define the problem precisely, isolate variables, accept calculated risk, and let data lead. In geopolitical terms, the legacy was equally enduring. Supersonic capability became a symbol of national competence. It signaled not only military strength, but industrial maturity and scientific depth. Countries that mastered high-speed flight demonstrated their ability to coordinate vast resources toward long-term technological goals. Aerospace became a strategic language spoken fluently only by those willing to invest patience, capital, and intellect. Yet despite its strategic and industrial consequences, the first supersonic flight remained, at its core, a human story. Chuck Yeager's role was not that of a mythic conqueror of the skies. It was that of a professional executing a mission within a carefully designed system. His success lay not in defying physics, but in trusting it, trusting the engineers who had shaped the aircraft, the scientists who had modeled its behavior, and the procedures that guided every second of the flight. He did not overpower the sound barrier. He passed through it because the machine beneath him was ready to do so. This distinction matters because it reframes how progress should be remembered. Breakthroughs are often romanticized as moments of individual brilliance or audacity. In reality, they are the visible peaks of structures built by many hands. The X-1 did not succeed because one man was fearless. It succeeded because fear was acknowledged, analyzed, and addressed systematically. As aviation advanced, this philosophy proved indispensable. Supersonic flight alone did not define the future. What followed, hypersonic research, spaceplanes, orbital vehicles, introduced challenges orders of magnitude greater. Heat became a dominant design constraint. Materials approached their limits. Margins for error shrank further still. The only reason these frontiers could even be approached was because the foundation laid by early supersonic research had proven that disciplined exploration works. Even today, as new generations revisit supersonic and hypersonic travel, the echoes of that first flight remain audible. Engineers still wrestle with shock interactions, thermal management, and efficiency trade-offs first identified in the late 1940s. The tools have changed. Computational fluid dynamics, advanced composites, artificial intelligence. But the underlying questions remain remarkably familiar. How fast can we go safely? How much complexity can we manage? What risks are acceptable in pursuit of progress? The answers continue to evolve, but the framework for finding them was established when the sound barrier fell. Perhaps the most profound legacy of the first supersonic flight lies in how it reframed limits themselves. Before that moment, the sound barrier was treated as a hard boundary, an invisible wall enforced by nature. Afterward, it was understood as a region. Dangerous, yes, but navigable with preparation and insight. This reframing applies far beyond aviation. Many of humanity's perceived limits exist not because they are absolute, but because they are poorly understood. History repeatedly shows that when knowledge replaces assumption, boundaries shift. The X-1 program did not promise comfort, efficiency, or commercial success. It promised clarity. That clarity changed everything. It allowed designers to move forward with confidence rather than caution alone. It transformed fear into parameters and unknowns into equations. In the decades that followed, aviation continued to evolve, sometimes dramatically, sometimes incrementally. Supersonic flight became routine for military aircraft and aspirational for civilian travel. Technologies came and went. Programs succeeded and failed. But the intellectual inheritance of that first flight endured. embedded deeply in how aerospace challenges are approached. The desert where the sound barrier was first crossed is quiet now. The aircraft that achieved it rests in museums, its surfaces no longer hot, its instruments silent. Yet its influence remains active, present in every aircraft that operates near the edge of the possible. Because the true achievement of that flight was not speed. It was proof that humanity could confront the unknown with humility, structure, and resolve, and emerge not unscathed, but enlightened. The history of aviation is not written by accidents of courage or moments of luck. It is written by steel shaped to purpose, by equations tested against reality, and by individuals willing to trust both. The sound barrier fell not because it was attacked, but because it was understood. And that is the enduring lesson. The history of aviation is written with steel, ingenuity, and the will to challenge limits.